Hello everyone. Today we will be taking a look at one amazing question from Theory of Computation on the topic minimum pumping length, or we can say pumping lemma. So given in the question is a language which is represented in the form of regular expression, and we have to find its minimum pumping length. So first we start by finding what are the strings included in the language. So we can see the language is 0 1 power 0 0 1 power 1 and so on. This is the basic definition of regular expressions I have applied here, and we have the strings in the language as null 0 1 0 1 0 1 and so on. So we can see one thing, that only even length strings including null are accepted, or you can say are contained in the grammar. No odd length string are there. So now we need to find its minimum pumping length. Now for that what we can do is we can take help from, we can either directly apply the definition of minimum pumping length, run the theorem, and then we can get it. But to make things more simple, we have one theorem, we have one important property of minimum pumping length, that is minimum pumping length will be greater than the length of the minimum string in the language. Now here the minimum length string in this language is null. That implies minimum pumping length will be strictly greater than the length of null. We know length of null is nothing, so minimum pumping length will be greater than 0, or we can say minimum pumping length will be greater than or equals to 1. Now we know by the basic definition that minimum pumping length is always greater than equal to 1, so we don't get any idea, or we cannot come to a conclusion that what will be the minimum pumping length be from this only thing. So we need to apply the basic definition. Let's take the minimum pumping length. Let's take it case say minimum pumping length to be 1. Now according to the definition, we need to take the minimum pumping length something, and then we define a positive integer p which will be equal to the minimum pumping length. And now whatever strings which will be belonging to L, and the strings whose length will be greater than or equal to p, must contain a subsection, a part pattern, or a substring which can be pumped any number of times in that string, and all those generated strings must belong to the given language L. This is the basic definition of minimum pumping length. Now we will start doing the process only. So we have defined p is equals to 1. Now that means our pattern length, or the subsection length, or the substring length can only be in the range of 1 to p. That means 1 to 1. That implies only 1. So let's start by taking a string length of 1. But we don't have any string length of 1 in our language because we only have even length string. So that means in this case our minimum pumping length test passes. Now let's move to string length of 2. String length of 2, we have one string that is 0 1. Now in this we need to take a pattern which can be repeated any number of times, and the string generated must belong to the language L. Now if we try to take this 0 as a pattern, we say that we can pump this 0 any number of times. That means we can pump it 0 number of times, 1 number of times, 2 number of times, and so on. So if we say that we pump this 0 number of times, that means this 0 will not be there, only 1 will be there. Okay, but this 1 does not belong to our language. That means this cannot be the pattern. Now if we take this 1 as a pattern, then a string will become 0, which also does not belong to L. And if we try to take the whole pattern 0 as 1, 0 1 as pattern, we cannot do that because our pattern length is restricted to only 1. So that means we cannot take minimum pumping length to be 1. We need to move on to minimum pumping length to be equal to 2. That equals to p. According to the definition, we define a positive integer as well. Now pattern length will be 1 to p. That means 1 to 2 means either 1 or 2 we can take. The basic definition says that only a pattern must exist. There exists a pattern. Means 0, not 0, only 1 or more than 1, 2, 3, 4. Any number of patterns can occur, but we only need one pattern in our string to satisfy the property of, to satisfy the definition of minimum pumping length. So if we consider string length of 2, Okay, so let me revise the basic definition. If p is equals to 2, now according to minimum pumping length theorem or lemma, we need to find all those strings of length greater than or equal to 2. So we start with string of length 2. We have one string that is 0 1 which belongs to L. Now we can take pattern of length 1 or 2, but we saw earlier that if we take pattern length of 1, we can that those strings don't belong to L, so we can directly take the pattern length to be 2. That means 0 1 0 number of times that is equals to null must belong to L. Yes, that is the case true. We have one string null which belongs to L. Now if we take 0 1 power 1, that is one number of time. 0 1 is a string which belongs to L. Okay, now 0 1 power 2, we have 0 1 0 1 which belongs to L. That means we have found a pumping length equal to 2, in which any string of length more greater than or equal to p have a pattern of 0 1, in this case, in the case of string length 2, and though that pattern can be pumped any number of times and the strings generated belong to L, hence our minimum pumping length is equals to 2 for this question. So the basic confusion in this question occurs when we don't know this thing, that what is the min pattern length we have to take for a given pumping length p. If we don't know this, then definitely many of us will answer p is equals to 1 or minimum pumping length equal to 1. So this is the most important thing here which we need to know. Okay, thank you.